Hello, this is Miss Moore, and today during chemistry we're going to talk about entropy. Today's essential question: what does entropy tell us about a chemical reaction? All right, we'll start with this question: what reactions actually occur? So it might seem like that exothermic reactions would actually occur because they need less energy to happen, right? You end up releasing energy. So it kind of makes intuitive sense, but those would be the ones that would, always occur. Versus an endothermic reaction, they may not occur intuitively because they need lots of energy, right? They're absorbing lots of energy to happen. So points 1 and 2 are intuitive, what we might think would happen. However, the statements above, while logical, are not necessarily true. There's a lot more to the story. And that brings us to entropy. So, entropy is the degree of disorder or dispersal of energy in a reaction or in a system. And we symbolize entropy as S. And we have a formula here that looks like some of the formulas we've been using so far, and that is the change of enthalpy of a reaction is the sum of the change in energy of the products minus the change in energy of the reactants. And by the way, this little, looks like a degree sign, the little circle means at standard temperature and pressure. So an increase in entropy is assigned a positive value. Okay, so if we have a delta S that it's positive, we have an increase in entropy, meaning more disorder or more dispersal of energy. So conversely, a decrease in entropy is assigned as a negative value. So if delta S is negative, we have a decrease in energy, meaning we have more order and less dispersal of energy. For now, think about a reaction that has a positive delta S is more likely to happen than a reaction with a negative delta S. Why is that? Well, it's easier to go towards more disorder, okay? It's easier to spill milk, now the milk's everywhere, more disorder, than it is to put it back in the glass. It's easier to mess up the house, more disorder, than it is to put it all back together and make it all neat. Okay, so positive delta S reactions for now, when we're ignoring other factors, are more likely to occur. Okay, let's talk about values of entropy. So a pure perfect crystal, meaning a solid, at 0K, which is absolute zero, meaning the absolute lowest theoretical temperature. So a pure perfect crystal at 0K is assigned an absolute entropy of 0. Okay? So this crystal is completely organized and completely ordered. No disorder, no dispersion of energy. Okay? Now the absolute entropies of substances in the real world, the one that we live in, at not 0K, are measured relative to that. And so they all have they all have values that are greater than 0. Okay, so the state of the thing we're talking about, meaning solid, liquid, gas, plasma, the temperature, the number of particles, and the volumes of gases are all important factors in determining the entropy or the state of disorder. Okay, and so with that, we find that solids have less entropy than liquids, which have less entropy than gases. That should make sense. Solids, the molecules in a solids are way more organized than the molecules in a liquid, and molecules in a liquid are way more organized than the molecules in a gas, and more spread out, right? Entropy of a small number of particles is less than the entropy for a large number of similar particles. And conceptually that kind of makes sense, right? If I have a few things in my room to keep up, it's much easier to keep them organized than if I have a whole bunch of things in that same room, right? And remember, small entropy means more organization, more ordered. Large entropy means more disorder. So the less you have, the more ordered it is. The more you have, the less ordered it is. Okay, entropies of gases with smaller volumes are less than entropy of gases with larger volumes. So everything else created equal, we have the same number, same temperature, same number of moles, same number of particles, whatever. There is going to be more entropy in a greater volume. Why is that? Well, because the gases have more room to move. They're going to move farther apart. Okay. Absolute entropy increases with increasing temperature. Why would that be? Increasing temperature is really increasing kinetic energy. Increasing kinetic energy means more movement. More movement leads to more disorder, which means bigger entropy. And entropy of more complex structures is greater than the entropy of less complex structures. Okay, let's try a little bit of practice. For this particular lesson, there's a little bit of math involved, but what we really need to focus on is the qualitative understanding, qualitative analysis of entropy. Okay, so what we're going to do with this problem here is predict whether the, wow, not entry, gotta love spell correct. How about the entropy change of the system will be positive or negative. All right, so our system here is we take two hydrogen gas and an oxygen gas and we produce liquid water. So the question is, are we increasing or decreasing disorder or entropy during this reaction? So there's a lot of things we can look at here. So first of all, we can note, that was kind of messy. Let's do this. That on a reactant side, we have gases. And on the product side, we have a liquid. So gases, are they high entropy or low entropy? They have a greater entropy, right? So high entropy, we'll say. Going to a liquid which has a lower entropy. More disorder, lower entropy. Okay, we could also look at the number of particles on the reactant and the product side. So on the reactant side, we have 2 moles of H2 and 1 mole of O2, which means we have a total of 3 moles of our reactant. And on the product side, we have 2 moles of reactant. And if you remember, more particles means more entropy. So high entropy for this too. And over here, that would be a lower entropy. One other we can actually see here is more and less complex molecules. All we have here is just H2 and O2. Those are less complicated or less complex than H2O. So with the type of molecules we have here lower entropy and higher entropy. But overall, what would you say? Are we going from reactant to product? Would you say we're mostly increasing entropy or disorder or decreasing it? I would say we are decreasing entropy, which means our delta S is negative or positive? It would be a negative. Okay, let's try another one. We're going to again predict whether the entropy change of the system will be positive or negative. So let's start with the state of matter. On our reactant side, we have a solid, which is low entropy. And we have gases on the product side, which it would be higher entropy. What else do we see here? We can look at the number of particles. We have 1 mole on the reactant side and 2 moles on the product side, which would mean we have lower entropy on the reactant side and a higher entropy on the product side. We're looking at the number of moles. So from this one, what do you think? Are we increasing entropy or decreasing entropy? Or another way to say it is, are we increasing disorder or decreasing disorder? Well, in this case, I would say we are increasing disorder. So our delta S is going to end up being a positive number or a negative number. Increasing disorder, positive. All right, hopefully you kind of have an idea how that works. All right, and let's just try one real quick math problem. Nothing major here. So we're going to use the standard entropy values in Appendix 3 to calculate the standard entropy changes for the following reaction at 25 degrees Celsius. Okay, and the formula we're going to use is delta S reaction equals the sum of the entropy of the products minus the sum of the entropy of the reactants. And from here, we just look some numbers up on the data table and plug and chug. So we will start with our products. So we're looking for HCl, and we know there are 2 of them. So it's going to be 2 times whatever is on the table. So let's check that out. So HCl, and by the way, we're looking here at our enthalpy, which is in joules per Kelvin mole. We have 187.0. So 2 times 187.0 joules per Kelvin mole. And that's it for our products. So now we need to find our reactants. So we'll start with hydrogen. We'll look hydrogen up, and our hydrogen is 131.0. 131.0 joules per Kelvin mole plus our chlorine, which is 223 joules per Kelvin mole. So all we've left to do is just plug this all in, and if I did my calculations right, I came up with 20, that's supposed to be a 0 there, 0.0 joules per Kelvin mole. So we ended up with a very small increase in entropy. And that probably makes sense if we look back at our equation here. Let me get rid of all this stuff. You can see that we start with a gas, two gases, and we end up with a gas. So really not much of a change in entropy there. We have 2 moles on the reactant side and 2 moles on the product side, so not much of a change there. The biggest change seems to be that we have 2 simple molecules going to one that's a little bit more complex, leading to a very small increase in entropy. All right, folks, that's it for today. Have a good one.